Okay, so today's notes are section 5.4b. It's on synthetic division, and we're going to learn how to divide polynomials using synthetic division today. We previously learned polynomial long division, but today we're going to practice synthetic division. Our language objective is to use the correct terminology to describe that process. So I'm going to jump right in by talking about why we're learning two methods for synthetic division, or for dividing polynomials, both polynomial long division and synthetic division. Why are we learning both? So first of all, synthetic division, what we're learning today is going to simplify the process, or we're learning it because it simplifies the process of dividing polynomials by omitting variables and exponents. So it's a lot cleaner looking. It's a lot simpler to see the steps, and it doesn't take as much space. It's not as tedious, but it only works when dividing by a linear factor. Which means a factor in the form x minus a, or in the form x minus a. So there can be linear factors that have a coefficient of x. So that means x needs to be to the first power, and it cannot have another exponent. So this means synthetic division will be super helpful when we're dividing by terms that look like this, x minus a. Our x are plus or minus some number, so that will make the process a lot easier. But if we need to divide by something that has x squared or 2x plus 5, then you're going to want to use polynomial long division. But this process is going to make your life a lot easier for these simpler ones. So the first thing I want to note is you always want to start by switching the sign of, this is not like why we're using synthetic division, but this is a key point of synthetic division. When we're using it, we're always going to start by switching the sign of a, because then we can add rather than subtract. So as you guys we're doing polynomial long division, you probably realize that the negatives and positives get confusing. This will hopefully resolve that problem. So you can add instead of subtracting. Okay, so let's jump in with an example. So I'm going to try to write this small so we have enough space. We're going to use synthetic division to divide x cubed minus 14x squared plus 51x minus 54 by x plus 2. Okay, so this is the problem we're going to do. Our first step, as we noted right here with the star, we switch sign of a. Which in this case is 2, so 2 becomes negative 2. So I'm putting a negative 2 here in this little corner box thing. And I'm going to write all the coefficients. So my next step, write coefficients of the polynomial. So my first coefficient is 1, my second coefficient is negative 14, my third is 51, and the last one is negative 54. Again, one thing you do have to pay attention to is if it skips degrees. This one does not, so I don't need to put placeholders, but just like polynomial long division, if it does skip a degree, you do need to put a placeholder of 0. So that's one thing to keep in mind. We don't need to worry about that in this example, but if it skips a degree, you do need to put a placeholder of 0. So the next step I do is I bring down the first coefficient. And in this case, that's 1, so I just bring that down here. And then I'm going to multiply the negative 2 by the divisor for each step. So in this case, I do negative 2 times 1, and I get -2, and I'm going to put that here. And then I add straight down. And when I do that, I do -14 plus -2, which is the same as -2, and I get -16. And then I'm just going to repeat that process. So then I'm going to do -2 times -16, which gives me +32. And I add that straight down, and I get 83. And then I'm going to do that again until I'm done. And if I multiply -2 by 83, I get -166. When I add that straight down, I get -220. So then I'm done that process. I can just write down, or my last step is to write the new polynomial. Sorry, I'm losing some space here. With new coefficients, 1 degree less. And then each variable 1 degree less. 1 degree less. So when I do that, I end up with x squared minus 16x plus 83, because I do 1 degree less and just carry down those coefficients, and I have a remainder of -220. So that will be my answer and we're done the long division, or the synthetic division. So I'm going to flip the page for a quick check, make sure you have this all down. So for our quick check, I want us to divide x cubed plus 7x squared minus 38x minus 240 by x plus 5 using synthetic division. So you pause this, try it on your own. I'm going to go over it now. So again, the first step is I switch the sign on the a value. So it was +5, so I'm putting a -5 in the little box. And then I write down all my coefficients. So I have x cubed is 1, x squared is 7, x is -38, and my constant is -240. And I'm going to carry my first coefficient down. I do -5 times 1, I get -5. I add those straight down and I get 2. -5 times 2, I get -10. I add those straight down and I get -48. I do -5 times -48, which ends up giving me +240. So then those cancel out. I'm left with a remainder of 0. So my new polynomial, or the polynomial I get when I divide this by this, is x squared, because I take 1 degree less, plus 2x minus 48. So that is the answer when I divide those out. If I wanted to write factored form of the polynomial, it would be similar, but we'd include the x plus 5 times x squared plus 2x minus 48. And we could factor this further, but we're not going to worry about that right now. Make sure you write down any questions, comments, concerns on this. There's one last thing I want to go over before we end our notes for today, and that's the remainder theorem. And this isn't a huge deal, but it can be useful in certain situations. So, I'm spelling down. There we go. The remainder theorem says that if you divide a polynomial by a linear factor in the form x minus a, then the remainder is the value of that function evaluated for that second term. So it's the remainder of p of a. So to demonstrate this point, I'm going to do a little example. I want us, or given that p of x is equal to x to the 5th minus 2x cubed minus x squared plus 2. I want us to figure out what is p of 3. So to do this, step 1, ultimately what we're going to do, so we're going to do a lot of sub-steps, but we're going to divide the original polynomial by x minus 3. So again, I just put in the form x minus a, so I'm dividing by x minus 3. One thing when I'm doing this, notice that it skips x to the 4th and x, so I need to put placeholders for x to the 4th and x. So I'm going to do that. Since I'm dividing by x minus 3, the number I put in the little box is positive 3. And I'm going to write down my coefficients. So for x to the 5th, I have 1. X to the 4th is skipped, so I put a 0. And then I have negative 2 x cubed, negative 1 x squared, 0 x, and 2. So those are all my coefficients. Note that I had to put zeros for the x to the 4th and the x. Draw my line, put my first coefficient at the bottom, multiply, and I get 3 times 1 is 3. So I get 3 there. 3 times 3 is 9. Add those down, I get 7. 7 times 3 is 21. Add those down, I get 20. 3 times 20 is 60. Add those down, I get 60. And 3 times 60 is 180. Add that down, and I get 182. So my remainder is 182. So that tells me that P of 3 would be equal to 182. If you're not quite sure about that, we'll check it using the traditional way of evaluating a function. So if I do P of 3 equals 3 to the 5th minus 2 times 3 cubed minus 3 squared plus 2. 3 to the 5th is 243. 3 cubed is 27 times 2 is 54. 3 squared is 9, and then plus 2. 243 minus 54 leaves us with 189 minus 9 plus 2, which leaves us with 180 plus 2, or 182. So in both methods, we get P of 3 is equal to 182. So that checks out. Our method works. So if you don't like evaluating with a lot of exponents and crazy polynomials, if you find this easier, that can be another way to evaluate for a value at a given point on the polynomial. All right, make sure you write down any questions, comments, concerns on any of these notes so we can go over them together in class.